Good evening, students. Are you able to hear? Yeah, can someone respond? Yeah, can someone respond?
Yes, sir.
Okay. So what was the last topic we were discussing? We saw electric field due to a dipole at an equatorial point, right? So let's get started. Yeah. So today we are supposed to discuss about an expression to find the torque due to an electric dipole when it is placed in an external electric field. Is that right? So that is our job. So how to proceed with it? Let's see. Okay. So if this force is QE, do you remember the concept that we discussed yesterday? You already have an electric dipole and you place it in an external electric field, and that electric dipole is making an angle theta with respect to the axis of the dipole. Sorry, with respect to the axis of the electric field. Now, what will happen to the charge Q? It will start experiencing a force QE. Then what will happen to the charge minus Q? It will also experience a force QE, but in the opposite direction. As a result of which, they form a system of equal and opposite forces, but not necessarily a system where the torque is zero. So what is happening here? The net force that is happening is always going to be zero. I've given it here. The net force on the dipole is zero. But what about the torque? It's a non-zero value. So for that, we need to recollect the concept of what is torque. So can someone tell me? What is torque, guys? Torque is also called as moment of force. But what is it actually? It is defined as the product of force and perpendicular distance from where? Perpendicular distance from the axis of dipole. Is that clear? So is it clear to people who are online?
Yes, sir.
Yes, sir.
Okay. Now see, let's say the axis of rotation is into the plane of the paper, and this point is at a distance of r. Okay. Then if I apply a force at this point, then how will you write torque as? Torque is equal to what? F cos theta into r. Where is theta? This one, huh? Where other one? This one. Okay, you want to draw like this, sir? Okay. Perpendicular to whom? No, that's not what the meaning is. No. What did I say? Force should be multiplied with the perpendicular distance from the axis of rotation. Right. So if I take the line along the axis of rotation, from the point of application of force, if I drop a perpendicular. Okay. And if I say the angle between force and r is theta, then this is also theta. Then how much will this distance be? It will be r sine theta. Then what is torque equal to? Force multiplied with r sine theta. Accepted. So this is in terms of magnitude. Okay, but there is another formula for torque which is also called as r vector cross f vector. Right? What is this r vector cross f vector? See, if r vector is like this and f vector is like this, then what is r vector cross f vector equal to? It is called as torque. But what is the direction of force experienced by it? So when you do the cross product between two vectors, how will you do the rotation? So from the first vector, you need to turn your hand towards the second vector in the shortest direction possible. So from r vector, you need to turn your right hand, curl the fingers of your right hand in the shortest direction possible. When you do that and extend your thumb, the thumb will give you the direction of resultant. So what is the direction of resultant? It is towards us. Is this point clear to everyone? Is it clear to everyone? So what I'm trying to say? So for people who are online, is it clear?
Yes, sir.
Okay. It is towards us. So having all these points in mind, let's get back to the derivation. So the force that is acting at the point of application is Q into E. Right? And the force that is acting at another point of application is other Q into E. Okay. Let's say the distance between the positive and the negative charges is 2D. Okay. Then the axis of this dipole is going to be at the center. Accepted? So if it is going to be at the center, then this distance is D, then the other distance is also D. Right? When it is going to be D like this, and this angle is going to be theta, how much is this distance going to be? How much will this distance be? It is d sine theta. So the force the torque exerted by charge number 1 is equal to how much? In terms of magnitude, it is Q into E into d sine theta. Right? Similarly, what is going to be the torque exerted by the second particle or the second force? That is also Q into E into d sine theta. Accepted? Right? When this is going to be the scenario, my job is to find in which direction they are aligned to. So if I take this as a vector and this also as a vector, tell me torque due to the first particle is acting in which direction? So a system is revolving in clockwise direction. So curl the fingers of your right hand in the clockwise direction and place your thumb extended. First is B and the second is at A. Okay. Think about it. We have to switch on the video for people who are online. Guys, are you able to see me?
Yes, sir.
See, what I'm trying to say is, listen to this carefully. This is how the charge particles, this is how the system is present. One force is acting in this direction. The other force is acting in this direction. Right? So the whole system about the center of axis will revolve in this way. So you can have your pen and try to do it. So with respect to you, it is going to be clockwise. With respect to, when I'm revolving, right, with respect to me, I'm able to see it is revolving clockwise. Whereas for you, it will appear as if it is anti-clockwise, right? So you have to see it from my perspective. So when it is revolving clockwise, right, this is the force. This is the point where plus Q is there. There is the force. This is R vector. So R vector cross F vector will be into the plane. So to put it in simple terms, you have a screw, okay? You know the difference between a screw and a nail. So nail is something where you hammer it, screw is where you rotate it, right? So if you want to send a screw into something, in which direction will you revolve? The best example is your water bottle cap. So if you see a water bottle cap, when you want to close it, imagine in which direction will you turn. By default, your hand will go, you'll not think. So you rotate it clockwise. When you rotate it clockwise, is the cap going away from you or towards you? Away from you. That is the direction of torque. So when you want to open the bottle, you're going to revolve it in the anti-clockwise direction, which is going to travel towards you. So to put it in simple terms, clockwise moments are negative. They are always away from you. Anti-clockwise moments are always positive. They are always towards you. This link is more than sufficient for you to solve any big torque-based problems. So please write down this hint. Clockwise moments are always negative, and anti-clockwise moments are always positive. What do I mean by positive? The object travels towards you, right? So having this point in mind, right, now try to answer what is the direction of torque exerted by the force at the first particle and the force at the second particle. I wrote only magnitude. Now, I told you many times, whenever you're dealing with vector, concentrate on magnitude. Direction will be taken care by the sign. So what is the torque due to first particle? I'm waiting for the direction. In which direction is the system revolving? What did I tell you? Just clockwise movements are always away from you. So if you look at the book, in your book, what is the direction this system is supposed to travel? It is away from you. So when it is away from you, can I say it is minus k cap? Similarly, the torque exerted due to the second force is also putting it into a clockwise movement. This is also going to be minus k cap, except. So what is happening here is, if you see the force due to force at the first particle is in the direction of I cap, force due to the second particle is in the direction of minus I cap. So that is the reason why they get cancelled. Whereas what happens in the case of torque, both the forces are supporting each other to put the whole system into a clockwise rotation. This is a very, very, very important point to be right. That is the reason why if you see the net torque is a non-zero value, and the reason why we are trying to derive only torque and not force. So towards us is positive. So torque towards us is anti-clockwise. Water bottle cap down. You want to open it, you want to bring it towards you, what will happen? Anti-clockwise. So it is positive. So the net torque is going to be equal to torque 1 plus torque 2. So what is the answer, guys? 2 times QE d sine theta, the whole torque as a resultant in the direction of minus k. Accepted? Now 2Q into d is what? Dipole momentum. So this will be PE sine theta in the direction of minus k cap, and this is going to be the net torque that is acting. And from here, if you want to write it in the vector product form, you write it as P vector cross E vector, and it is not equal to E vector cross P vector. Okay, always have this in your mind. So the net torque acting on the system has two formulae. What are they? If you write it only in terms of magnitude, it is P sine theta. If you write it in terms of vector product, it is P vector cross E vector. Okay, please make a note of it. Actually, it is only a 4-step derivation, but you need to know the basics. Is it clear? Shall I move on to the next concept? Did everyone copy it, guys? Should I go? Yeah. Yes. So the next important topic that we are going to discuss is called as electric flux. Okay. So what does electric flux mean? It is basically the number of okay. So if you consider a closed surface in a non-uniform electric field. Okay. But before that, I wanted to mention one important point. So here, if you see the heading, torque is experienced by dipole when you place it in uniform electric field. The question is, what will happen when you place the same dipole in a non-uniform electric field? You can't. You can, but I don't want the mathematical expression. I want to see what will you be able to observe. So force will be a non-zero value. As a result of which, in addition to experiencing torque, so torque will always put the system into a rotational motion, whereas force will put it in a translatory motion. So what will happen to the system is, the system will have a combined rotational plus translational motion. Please make a note of this point. Write it as an important note. Before electric flux, write it down. Write it as an important note. When an electric dipole is placed in a non-uniform electric field, when an electric dipole is placed in a non-uniform electric field, in addition to torque, it also experiences force.
Sir, can you repeat?
Yeah. So from where should I repeat?
Sir, from the first.
Okay, when a dipole is placed in a non-uniform electric field, in addition to torque, it experiences force, which will put the dipole in a combined rotational plus translational motion. Just give me a minute. Okay. So, yeah, that is all about a dipole placed in non-uniform electric field. So the next concept that we are going to discuss is called as electric flux. Okay. So when I talk about electric flux, it mainly speaks about the number of field lines that are passing through a given area perpendicular to it. That's it. That's the simplest definition. So instead of telling the statement every time, so we discussed one of the properties of electric field lines. What was it? We understood the concept that if the number of field lines are more at a particular place, then magnitude, the strength of the electric field is more at that location. But every time you can't keep using the word number of electric field lines. So instead of that, you need a particular word to determine that factor, and that is what is called as electric flux. Okay. So when I talk about electric flux, right, it is something like this. It is defined as the total number of electric field lines crossing through a given area. Just add this perpendicular to it. So please write down this definition. Electric flux is defined as the total number of which field lines? Electric field lines passing through a given area perpendicular to it. Okay. So for this, yeah, again. So you need to understand how to calculate the aerial vector. Okay, I'll come to that point. Listen. So listen. If at all I take my hand, okay, right? This hand has a particular area associated, right? For this area, will you be able to assign a direction is what the question is. So generally, what is area? Area is basically a scalar quantity, right? But here, the question itself is like, can you give a direction to this area? Will you be able to do it? Yes, you can do it if you follow certain rules. It comes from the cross product of vectors. Okay. So what generally happens is, if you take a particular surface, the direction of area for that particular surface will be the direction perpendicular to it. In the sense, this is a very, very important point. Note it, okay? So this is a two-dimensional shape. Okay, if you ignore the thickness of my hand, I can call it as a two-dimensional shape, like a plane shape. So for my palm, the direction of aerial vector is going to be like this. It is perpendicular to it, but it is away from it. In a similar way, if I take the aerial vector here, it is again away from it, right? Similarly, if I take my mobile phone, right? If I take my mobile phone, it is actually taking the shape of a cuboid. This is a three-dimensional shape. So for a three-dimensional shape, what is going to happen? It is a combination of 6 sides or 6 two-dimensional shapes. 6 rectangles is what is a cuboid, correct? So for this surface, what I can do is, I can find the aerial vector in this way or in this way. Means the aerial vector for my screen can either be in the upward direction or be in the downward direction. But which direction is right? So if you take, it should be in the upward direction. Why? Because I told you one important point. Aerial vector is perpendicular to a two-dimensional surface. In which direction? In the direction perpendicular to it, but it should be outside the surface. So it should not go into the surface. In a similar way, if I take this side where my charger is connected, this side, if I take it, what is the direction of electric field? Sorry, the direction of aerial vector. Is it towards you or towards me? Towards you. Right? In a similar way. Which point of view? No, that's the thing. In this case, it is towards you. This arrow mark is pointing towards you. So this is the direction of aerial vector. This, yeah, that's what you see from any end. It is towards you. Even if I say, I'm saying it is towards you only. This is the direction of arrow. Okay. So that disturbance will come only in the case of rotation, because anti-clockwise and clockwise. Here it is only a unit line, so it will not. Are you guys able to understand what I'm trying to say? So now read the definition, you will understand things better. Why area is involved? What are they trying to say? Out. No. They'll not get cancelled. See, if something has to get cancelled, they need to be of equal magnitude. No? They'll get cancelled. But there will be no point where area is alone taken into consideration, because we are not dealing with surface areas and volumes. We are dealing with electric field lines combined with area. So they'll not get cancelled. Okay. So if this point is clear, I would like to show you how to derive things. Right. See, for example, let's say there is a set of uniform electric field. Okay. And this uniform electric field is passing through an area like this. It is actually a circle, but when will a circle look at the shape of an ellipse? When the circle is sharing the planes. When it is, so if you see like this, it's a circle. If you see like this, it's an ellipse. Okay. So this is going to happen. And at this point, what will be the direction of aerial vector for it? It will be in the outward direction. So whenever you talk about a two-dimensional shape, aerial vector can be considered in any direction. You're free to do that. Okay. And this is the electric field. Then if I say the angle between electric field vector and aerial vector is theta, what does the definition of electric flux tell us? It is the number of field lines which are passing through a given area perpendicular to it. So note this point clearly. Perpendicular to the surface is the same as parallel to aerial vector or area vector. Think about it. Means if I take this arrow mark, I'm saying it is perpendicular to the surface, but at the same time, it is in the direction of aerial vector. Aren't they guessing? You're able to understand? So E vector is like this, means E can be resolved into two components. What are they? E cos theta and E sin theta. Correct? Then which component is in the direction perpendicular to the aerial vector? Sorry, perpendicular to the surface. Sorry. E cos theta. So if you take the product of E cos theta and aerial vector, this is what is called as electric flux. Okay. If you take the product of aerial vector and E cos theta, it's what is called as electric flux. So electric flux is basically a scalar quantity because you write it as E vector dot A vector. Isn't it the same as E cos theta? You're able to understand? So that's what happens.
So if area vector is around the electric field, then cos 0 is 1 to E.
Yeah. Right. Shall I proceed? Right. So let me see if there is a problem based on this one. So there are some important problems. Okay. Let's try to solve them. Now, let's try to solve 1.12 first, then we'll go to 1.11. Think about it, okay? So an electric field is uniform. So wherever you see uniform, what comes to your mind? That they are set of parallel lines. So electric field is uniform and it is in the positive x direction for positive x and uniform with the same magnitude but in negative x direction for negative x. What does that mean? So positive x belongs to which quadrant? Only first. First and fourth quadrant means in first and fourth quadrant, the direction of electric field is in the direction of positive x axis. That is the indirect meaning of that question. Though they use the word, it is negative x direction for negative x. What is the meaning? So in the second and the fourth quadrant, it is in the second and third quadrant, it is in the negative direction. Is that clear? Okay. And what is the magnitude of it? Its electric field that is given is 200 I cap Newton per coulomb for x greater than 0, and E is equal to 200 minus I cap or minus 200 I cap Newton per coulomb for x less than 0. Is the question clear till this point? Are you able to visualize it? Right. Now what they did is, there is a right circular cylinder of length 20 centimeter and radius 5 centimeter, which has its center at the origin and its axis along the x-axis, so that one face is at x is equal to plus 10 and the other is at x is equal to minus 10. So what is the meaning of it? The diagram is there. So if at all the diagram was not given, let's try to draw it on our own. So we have a cylinder, okay, and the cylinder's center is at which point? Origin, and its Zoom got closed. Why it is not coming here? Some internet issue. Over there. Ah, now you're able to see, no? So it is at the origin, and the axis is along the x-axis, right? So in this direction, what is the electric field? 200 I cap. In this direction, it is 200 minus I cap. Okay. So if I draw a perpendicular like this, now what are they expecting us to calculate? Their faces are at x is equal to plus 10 centimeter. So this point, if I take it as origin, the face is at a distance of 10 comma 0, and it is at a distance of minus 10 comma 0. So that the total length put together is 20 centimeters satisfied, and its radius is how much? 5 centimeters. So having all these points in mind, what is the net outward flux through? Repeat the question. What is the net outward flux through each flat face? So where is the flat face? So what is it we need to calculate? So for you to calculate flux, what are all the required parameters? You need to know the electric field and the aerial vector. So what is flux equal to? E vector dot A vector. So what is E vector for the right hand side? If I call this as phase 1. So flux through the first surface is how much? 200 I cap dot, what is the radius of that flat surface? Area. Area of that flat surface. What shape does that flat surface take? Circle. So what is pi r square? So 25 pi, it is in terms of centimeter. Okay. So 25 pi into 10 power minus 4 meter square. But this is in which direction? So by the logic I gave you, you tell me it is in which direction? It is in the direction of I cap. So 200 into 25 into this thing. So 25 into 2 is 50 pi into 10 power minus 2 I cap dot I cap is going to give you 1. 50 pi into 10 power minus 2 Newton meter. Sorry, Newton meter square per coulomb is what is going to be the value of electric flux through the first flat surface. But what is their expectation? They want the net outward flux through each flat face. So we calculated through the first one. Second one, I'm giving you 1 minute time. Calculate it fast and tell me what is it. Do it fast. Right, wrong, right. Calculate it for the second surface, second flat surface. That is on the left hand side. Huh? I don't know. It will be same. Why? Because E2 vector and aerial vector are again in the same direction, and their magnitudes are also same. So what will happen? Minus I cap dot minus I cap will come. Hence the answer will be 1. So you're able to understand 200 minus I cap dot 25 pi into 10 power minus 4 minus I cap. So when you multiply these two, 50 pi into 10 power minus 2 Newton meter square per coulomb is what is going to give you the flux. It's the same thing. Now comes an important question. What is the net outward flux? Sorry, second one is what is the flux through the side of the cylinder? So when you take the side of the cylinder, you take any small portion on top of it. Okay, the side is curved. So you take a small portion on top of it. What is going to be the direction of aerial vector? It is perpendicular to the electric field. Are you guys able to visualize what I'm trying to say? So if there is a curved surface, the aerial vector will be perpendicular and the electric field is in the x direction. So they both are perpendicular to each other. Hence, the flux through the curved surface is equal to 0. So EA cos 90, which is going to be 0. So what is going to be the net outward flux? So what is the total flux through the surface? Add it algebraically. So it is 100 pi into 10 power minus 2 Newton per meter square. So 100 and 10 power minus 2 will get cancelled. Answer is pi. So answer is 3.14. Correct? Huh? So 3.14 Newton meter square per coulomb is what is going to be the net flux through this particular surface. The D part we need not do because I didn't explain you Gauss law as of now. First, we need to master this flux calculation. Clear? Next. This is a tricky problem and a very important one. Okay. So mark it as important and try solving this. So one data that is missing in your textbook is this distance is A. That is the only thing that is missing. Remaining things you guys calculate. Those who are online, am I clear? Any doubts? Try this. So the electric field components in figure 1.27 are Ex is equal to alpha into x power half. And electric field along y direction and z direction are completely zero. Okay. In which alpha is some constant whose value is 800 Newton per coulomb per square root of meter. Okay. Calculate the flux through the cube and calculate the charge within the cube. Second part, forget. So first part alone, do it. Try it. Okay. So how many sides are there, guys? 6, right? So the number of sides is equal to the number of times you need to find the flux value. So if they ask you about each surface, you need to calculate 6 times. If they ask you the total flux, add all those 6 values. How will you add them? You need to add it algebraically. What is the meaning of it? Algebraically is right, but what is the meaning of it? You need to take the sign of the flux into consideration. Fortunately, in previous problem, what happened? Both the flux came out to be positive, but there is a possibility where flux can be negative also. When will it happen? When theta is equal to 180 degrees. You have to understand. So at that point, you need to be careful. In this problem, there is a high possibility that you will have a negative value also. Look at the areal vectors they have given. They have given you n r cap and n l cap, right? N is normal, r is right. So normal vector in the rightward direction and normal vector in the leftward direction, cap is what is given here. Okay. So please make a note of it. Try solving it. Anybody with the answer? I'm assuming that the first step is clear. Ex is equal to alpha into x power half is there, right? What is that x doing there? That is the first thing you need to crack. Okay, I'll come to that. What is going to be the coordinate of this point? A comma 0 comma 0. What is going to be the coordinate of this point? 2a comma 0 comma 0. Okay, having this in mind, you need to write the electric field at the first surface along x direction is going to be equal to how much? Alpha into, in the place of x, what will you substitute, guys? A power half. And it is in which direction? It is in I cap direction. How many of you did this? You did? So electric field along x direction at the second point. Alpha 2a power half times I cap. Okay. So electric field in all the other four surfaces is going to be 0. Right? Then where is the electric field? Then which electric field is actually contributing to the total flux? It is the total flux is existing only through the first and the second surface. For all other surfaces, the electric flux is going to be 0. Why? Because Ey is 0 and Ez is 0. So along y direction, there is no electric field. Along the z direction, there is no electric field. Right? So what is the flux through the first surface? Alpha into a power half I cap dot, what should I write? A square minus I cap. Accepted? Because a square is happening in minus I cap direction. Correct? With so it is alpha into a power 5 by 2 minus I cap dot I cap is going to be minus 1. So minus alpha into a power 5 by 2 Newton meter square per coulomb is going to be the total flux through the first surface. What about the flux through the second surface? It is equal to alpha into 2a power half times I cap into how much? A square I cap. So how much will this value come out to be? Root 2 alpha into a power 5 by 2 into 1 is going to be the total flux. So what is going to be the total flux here? Phi 1 plus phi 2. So what is going to be the value? Alpha into a power 5 by 2 into root 2 minus 1. This is going to be the value. So a power half into a square. Base is the same, powers will get added, no? A power half into a square is a power 5 by 2. Got it? Exponents, yeah. So alpha into a power 5 by 2 into root 2 minus 1 is going to give you the required answer. Clear, guys? Right. So alpha value is given to you, a value is known. So substitute everything and you try to calculate, the value comes out to be 1.05 Newton meter square per coulomb. Okay. So 75% of the chapter is over with this. The next topic that we need to concentrate upon is, if you're clear with this, I'll proceed. Those who are online, are you clear? Okay. Those who are here, are you clear? Right. Perfect. So now let's move on to the next concept that is called as Gauss law. Okay. So write down the heading as Gauss law and explain about the Gaussian surface. Okay. So we saw a concept where you're able to calculate the total number of field lines and speak about the strength of a particular electric field at a given location. For that, what will you use? You will speak about electric flux. But now the question is, what is the source which is generating that amount of electric flux is what we are interested in. So is there a connection that is going to exist between a concept of number of field lines and the charge that is producing it? Is what this Gauss law says. So if you read the statement, the law relates flux through any closed surface and the net charge enclosed within the surface. What does it do? It speaks about the relation between any closed surface and the total amount of charge that is present within the surface. Okay. And the statement. So here they say the law relates. It's not the statement. But the law statement is something like this. Law states, please write it down. Gauss law states that the total electric flux. Gauss law states that the total electric flux through any closed surface. Gauss law states that the total electric flux through any closed surface is equal to 1 by epsilon naught times is equal to 1 by epsilon naught times the total charge. So I'm not exactly telling the same thing. So listen to me and write. What did I tell? 1 by epsilon naught times the total charge enclosed by the surface. The total charge enclosed by the surface. Which surface? The closed surface that we are trying to talk about. So flux is mathematically written as, this is the actual meaning. Total flux is equal to 1 divided by epsilon naught times the total charge enclosed by the Gaussian surface. So you write it as Q enclosed, ENC. Everyone understand? So what I'm trying to tell here is, if you know the total flux, then if somebody asks you, can you calculate the total flux through that area, will you be able to calculate it? Use a simple mathematical equation, you're going to get the answer. Okay, you need not worry about how it is derived and all those things. There is a statement, just follow it. Okay. Next is, we saw what is Gauss law. The next thing that we are supposed to see is what is a Gaussian surface. Okay. So Gaussian surface is something like this. It is a closed, so you talk about any closed imaginary surface which follows a specific condition. Okay. A closed imaginary surface is generally called as a Gaussian surface. And in most of the cases, we consider the Gaussian surface to be three-dimensional. Okay, it is a three-dimensional shape. Is it clear till this point? So what does the statement tell us? Listen, if I have a system like this in some random shape, and I have charges Q1, Q2, minus Q3, Q4, and Q5, and minus Q5, for example. If I have a system like this, if I ask you what is the total flux through the surface, what will you say?
1 plus Q2.
Yes, it is Q1 plus Q2 minus Q3 divided by epsilon naught. Why didn't I take Q4 and Q5? Because they are outside the surface. According to Gauss law, the charges which are present inside the surface will only contribute. Is that clear? So keeping this in mind, we can say that Gauss law tells us that the flux through a closed surface depends only on the value of net charge that is present inside the surface, and it does not depend on the location of the charges. Secondly, it does not depend on the charges that are present outside the surface. This is a very, very, very important point to be noted. Okay, so there is a very important point to be noted. It will not. It can. Okay. Now, there is another way of writing Gauss law. other expression for Gauss law. Please write it down. It says something like this. This side, it is clear that net charge enclosed divided by epsilon naught. But left hand side, the flux parameter is there, right? What is the flux constant, flux value I told you? E vector dot A vector, right? But sometimes you will not have areas which are regular in shape. So whenever you have irregular shapes, right, the only option for us to solve it is by using calculus. So here you will say integral of E vector dot delta A equals, I will write it as dA vector is what is equal to Q enclosed by epsilon naught. But here one point I would like to mention, you put a circle around this integral. You call it as loop integral. Why we call it as loop integral is because you're integrating the area. Generally, there are two kinds of integrals. You put something like this is called as line integral. This is a part of your curriculum. Integral. In line integral, what you do is you calculate, integrate basically means adding. So you integrate distances to get area. Whereas in loop integral, what you do? You add small areas. You will not add distances. If you add all those areas, you will get a bigger area. That is why we call it as a loop integral also. Some books refer to it as surface integral. Is that clear? So this is another way of representing Gauss law. So this is one of the basics that we need to know before we study the next important concept, that is the applications of Gauss law. So there are three applications that are going to be there. So one point we understood, what has happened is, where is Coulomb's law applicable? When can you start applying Coulomb's law blindly? You have point charges. What happens when you have extended charge? The question is, aren't you supposed to apply Coulomb's law for extended charges? The answer is, you can apply it, but it is a tedious process, because you need to see, suppose you have an extended charge. An extended charge is basically collection of infinite number of point charges. Think about it. So you take your pen, for example, that pen is a collection of infinite number of small particles, right? So for you to apply Coulomb's law, you need to take one of such particles. You need to calculate the electric field due to that particle and then integrate it, which is a very big process. In order to overcome that, what has happened is Gauss law will be used to calculate the expression for what? Gauss law is used to calculate the expression for field for extended objects where there is a symmetry available. Symmetry in the sense, there is a particular pattern that is available to us. We will be able to apply this particular equation which I told you. This equation to solve them with ease. Okay, though here also you can ask me, sir, here also we are using surface integral. But trust me, you will get the answer in 3 steps. The same thing you have to do using Coulomb's law, it will take at least 10 to 12 steps. And it is tough also. You have to understand? So that is the reason why we are studying the applications of Gauss law. And if somebody asks you what application are you going to do, your job is to calculate what? Derive an expression for what? Electric field due to extended charges. So when I talk about extended charges, there are 3 applications. One is a linear charge, surface charge, and volume charge. That's the logic: 1-dimensional, 2-dimensional, 3-dimensional. Okay. So for that, there are certain steps that you need to follow to derive them. I'll give you those algorithms. So the process which I'm going to give you is applicable not only for these applications, you can use it to solve any problem based on Gauss law, whether it is electrostatics or magnetics. Okay. So that is what we are going to start with in tomorrow's class. So tomorrow I'll try to. Tomorrow I think I can complete. Okay. Tomorrow I think I can complete only 2 derivations maximum. By Monday I'll complete this chapter. Okay. So this week what I'll do is I'll give you an assignment which is based on all the topics that we have completed, which will include the other part also. The questions based on the topic we are supposed to discuss on Monday alone you can hold, others try to solve them. Okay. And the week following this week, we'll have a test. We'll have a 35 marks test based on this chapter. It's a subjective test. Okay. So I'll give you the schedule for it. Apart from that, any other doubt from today's topics? Any other doubts, guys? Can I assume things are clear? Okay, that's it from my side. I'll see you all tomorrow. Those who are online can leave.
Thank you, sir.
Yeah.